I think it's possible for us to cut down the amount of time we spend doing automated testing of software by over 90% without reducing the quality and consistency and completeness of our testing. Today I'm going to introduce to you a new software project called testtrim that is attempting to do this. This is a project that is still under development, but I'm hoping to share a little bit about the development so that I can get input and feedback from the community, as well as entertain and interest people with the technical work that's going on. I'm going to record two versions of this video. One will be a really short, sort of YouTube friendly, in that 10-minute range video that allows people to get a really quick introduction to what the project is. This is going to be the long version of introducing testtrim. So I'm going to go through a lot of technical detail on how the project works, but let me give you a really high level overview. The idea behind the project is that we're going to use code coverage data. That is the kind of instrumentation that you usually use to identify how much of your project is being covered by automated tests. We're going to use that information in order to identify what code each test executes. And then we're going to use information from your Git repository in order to identify what changes have occurred. We're going to merge the two together, and we're going to get the test suites that need to be run in order to test the changes that are being made. I recently left a job where we had software projects that took over 24 hours to execute their test automation suite. And that allowed us to develop software with a high confidence that we were delivering quality software to our customers. It was kind of a manageable problem that we found different solutions for handling, like running a lot of software testing in parallel or batching changes together so that we would be putting 2 or 3 changes into the same 24-hour test cycle, or even manually at times targeting tests, saying we're going to run this set of tests or this set of tests on this change. These were all solutions that we were able to use to manage that 24-hour test automation problem. But the core of this problem was that we had screwed up our testing pyramid. While in an ideal world, you would have a lot more unit tests that are fast and easy to run, that form the basis of your software quality, your software test automation suite. We ended up developing a lot more UI tests and end-to-end tests. And I think that this is a fairly easy problem to fall into, kind of a natural issue to have. Having this large quantity of tests was okay for the most part, but there were a few things that kind of really bothered me in the end. One of those things was we would have flaky tests. So flaky tests were situations that were particularly common in our UI tests, where a test library would fail to run successfully, and an engineer would look at it and say, well, this test is not relevant at all to the change that I'm making. Therefore, I know that it's not caused by my change. That was a really frustrating situation to be in when your test failed to merge or your change failed to merge because of a test having a flaky behavior to it. And the other thing I noticed is there were times when we were running these 24 hours of build and test automation for files that weren't even going to be tested by the test automation. So common case, the first case that comes to mind to me when I think about this is translation files. Our software was translated into dozens of different languages, and our test automation suite ran entirely in English. So why is it that if somebody made a typo correction in the French translations for a single word, we were going to run 20 plus hours of test automation over English software? The two problems together started to make me think deeply about the waste of this system. Even though we were able to manage it and provide the right business outcomes, it felt like we were being quite wasteful because we were often running tests that had nothing to do with the changes that were being made. So I had these problems on my mind one day when I was doing some work on my home server. My home server runs NixOS, and I noticed that the NixOS system wasn't performing regular scrubs of its RAID array. While I was trying to resolve that problem, I came across how NixOS does testing, and the two thoughts converged in my mind to prove to me that there's a better way to do this. So let me show you a little bit about how NixOS does testing. A little bit of context. NixOS is a Linux distribution with a declarative configuration approach. So for typical cases where you're distributing a package, for example, with NixOS, you're going to tell it, here's the source code that I want you to package. Here are the commands that I want you to run to turn that into a package. And then you're going to throw it into Nix, and it's going to do a bunch of magic and come out with a package. The really neat thing about it is that if you don't change any of those inputs, Nix is able to take a look at your declarative files and say, I already have a package that used those inputs and performed that process and created that package, so I don't need to do it again. They've taken that concept and they've applied it to how they do testing as well. So what we're going to do here is we're going to run a NixOS test. So let me show you the test that I wrote to solve, to verify that my RAID array scrub problem was solved. This isn't going to require a deep dive into understanding Nix syntax. I'll just give you a really quick overview. We're going to verify that there's an MD check systemd unit, and we're going to see if it's active or inactive. We're going to create a RAID array, yada, yada, yada. It isn't really too relevant here. So what I'm going to do here is run that test. Having run that test, it successfully went through all those steps of setting up a virtual machine and running the test script, and it ended up taking a total of 136 seconds to execute. Now, here's the really cool part to me about the NixOS tests. I'm going to run the exact same command again, and what's going to happen is it almost instantly just outputs the path of the built test package. Nix was able to identify that none of the inputs to that test had changed since the last time I ran it, and that test already had an output in its Nix store saying that it had completed successfully, and therefore I'm done already. So why can't all software test automation work like this? Why can't a normal software test realize that I haven't changed anything that's relevant to the test that's being run, and therefore I can use the result from my last test run? Well, there's really a lot of difficulty with doing that, but is it difficulty in the sense of these are problems that can be solved, that we can build up tools layer by layer, brick by brick until we get to a solution? Or is it difficulty in terms of halting problem difficulty, NP problem difficulty, where it's probably just kind of unsolvable? I don't know. To be totally frank, I'm not totally sure. Let's take a little bit of a look into what I'm planning to do with my testing tool called testtrim, and then I'm going to demonstrate to you the software in a working state today, in a working but extremely limited state today. So here's a side-by-side view of some of these basic math functions and some basic test cases for them. And I think that as a human, it's really easy for us to identify that this test add function tests the functionality of this add method, and this test add decimal tests this add decimal function, and so on. So the idea behind testtrim is if we were using a test coverage tool, a tool that was running these tests and monitoring what functions and files that they touched and executed while they were running, we would be able to know that test add uses the add function and test add decimal uses the add decimal function. And then if we combined that with a source control diff, for example, here a git diff, we would be able to see that while we were making this change, we did not modify the add function. And so we know that we don't need to rerun the test add test. That's the basic concept here, is that we're going to use a combination of coverage data that's gathered on tests and Git or other source control management systems change management, merge the two to be able to see what tests we actually need to run in what situations. Let's take a look at testtrim working in this demo project. So this project has basic ops, which has a bunch of really simple mathematical functions, adding, subtracting, multiplying, dividing, very uninteresting functions. And then it has some slightly more complex functions like a Fibonacci sequence and a factorial here that use some of those basic operations, the addition, the subtraction, and the multiplication. So testtrim operates in two modes. It operates in one mode where you're on a clean working directory, in which case it's going to create a new coverage map and save that in its database. And then it also operates in a second mode once you're in a dirty working directory, where we'll use any saved coverage maps to identify what kind of tests need to be run. So we're going to run it first of all in a clean checkout of main. Okay. So I'm going to run it with a fairly verbose output here so that we can see what tests are being run. When I run this for the first time, it's going to say, I didn't find a base commit identified with coverage data to work from, and then it's going to execute every test in the project. So if you take a closer look here, we can see that we're running a test out of source lib.rs, and we're running sequences, tests, test Fibonacci, for example. I believe there's 8 total tests in this project, and it ran all 8 tests. Now, if I pop into my editor and I make a change to one of these tests, factorial of 0 and the factorial of 1 is -1. Then when I run testtrim, what it's going to do is, ignoring the fact that the test failed, that's kind of the irrelevant thing. Obviously, the test failed because that's not the right definition of a factorial. But it's able to look at the previous commit of data that I had just run. And now it says that I have only 2 relevant test cases out of my total 8 test cases in this suite. And I'm going to run that 25% of those tests. And then, of course, they're going to fail. If I revert the factorial function back to its normal state, but maybe instead I put a documentation comment on this function, then when I run testtrim again, I'm going to get the same output, which is that I have 2 test cases that have been executed as opposed to all 8, but this time I've successfully run my tests. So you'll notice a couple things straight off the bat. That comment isn't the kind of thing that should have functionally mattered. Here, testtrim does currently think that those comments are relevant, but despite that, it's at least able to identify only a subset of tests need to be run as opposed to all tests, which is an improvement. In this case, we're saving 75% of our test run. There are basically 3 parts to testtrim's functionality today. One is when it runs tests, it runs them with independent coverage output. So the tests are instrumented, and then they provide information about what functions and files they executed on a per test basis. 2 is we take a look at, using the source control system, what changes have been made since the last time we ran a test. And 3 is we identify the last time we ran a test by saving that coverage data into a database. Between all of those pieces, testtrim is able to target what set of tests need to be run for a specific change. Let's run a little bit of a demo with a larger project. If you've never heard of ripgrep before, you really should have. It's an amazing tool. It acts as a replacement for grep, but it is so much faster. And it is one of the few test projects that I've been using to run testtrim against to see how effective it's going to be. So what we're going to do to give you a quick demo is I'm going to take a look at the git log for ripgrep. Then I'm going to go back a couple commits here, and we're going to work with this 8bd commit. I'm going to run testtrim here. This should run against all tests because I haven't stored this data in my database yet. Excellent. We were able to successfully run all the tests. Now I'm going to check out master. And if I run testtrim again, it's going to do its computation based upon that 8bd595 commit. And here it identifies that now in the couple of commits since then, I've made enough changes that I need to rerun 434 out of 1087 tests for 39% of the tests. So there's some examples of testtrim running. I'm going to give you a deep dive now into the testtrim project as it exists today, with the intent of showing you exactly how it operates, which will really be about highlighting the limitations and the restrictions and the places where it's kind of incomplete today, before we move on to what does the future look like. Okay, so I guess the first and most obvious thing is that testtrim is a Rust project. The reason that it is a Rust project is, this is kind of just a personal choice, right? I like programming in Rust. I guess there's not much more to it than that. All right, there's a couple of pieces of testtrim that I would call kind of the meat of it, the interesting parts. Those are what I wanted to go through and talk about a little bit. The first meaty part of testtrim is its get target test cases function. This is what coordinates all the interesting pieces of functionality of this tool. First of all, you'll notice, particularly if you can read Rust code, that there's a lot of generic types being used here. The main thing that we're generic over, that we have multiple potential implementation paths or at least stubs for in the future, different source control systems. So currently all of this functions on Git, but maybe in the future it could work on another source control system, and test platforms. So right now testtrim operates entirely on Rust projects, but I think that the concepts here are certainly applicable to other projects, and I've developed that in a way that it is plug-inable for various different test platforms in the future. The get target test case command, first of all, it uses the test platform to do test discovery, to get all of the test cases. In the Rust platform case, that's internally running a cargo tests command in order to compile all of the code and list all of the test binaries and all of the test cases that they have. Then what we're going to do is we're going to search for an Ancestor commit that has coverage data. The way that we find the Ancestor commit is basically by looking at the head commit and then checking the database for whether it has coverage data for that commit. And then if it doesn't, we go backwards through the commit history to the next commit and we look for whether it has coverage data. We're trying to identify when was the last time you ran testtrim in a way that generated coverage output so that we can use that to identify the tests that need to be run. So the tricky part of looking for the Ancestor commit is what happens when there are branches, or rather in the case of looking for Ancestor commits, what happens when there's a merge commit. So hypothetically, if this is our head commit that we've started at and we start to look for its Ancestor, we're going to go up to this commit, which is a merge commit. And in an ideal world, this commit has coverage data. I would expect that a merge commit into a main branch would typically have tests run on it, and so they would have coverage data. But hypothetically, if this commit didn't have coverage data and we wanted to keep looking for the next nearest Ancestor, well, we have a problem in that this merge has two potential parents. While we can look at both parents, the real core of the problem is that I don't know which of them is going to have coverage data that is relevant and useful to verify or to analyze for relevant tests. So testtrim, for the time being, how it works is it goes up to the nearest common ancestor of these commits. So basically, we will ignore this commit, we will ignore this commit, and we will go to their common ancestor, which is this commit here that we labeled as merge base, and it will check whether merge base has any coverage data. And it will proceed in this fashion, going through all of the parents of the commits until it either finds a commit with coverage data or it finds a commit that no longer has any parents. So it's possible that we haven't found an ancestor commit. In that case, this would be testtrim being run for the first time. We'll just run all of the tests. But if we do have an ancestor commit, then we'll use that coverage data to identify what relevant test cases there are to run. That currently works entirely based upon the source control's changed files. So we'll take that ancestor commit and we'll take the current working tree and we'll diff the two of them. That'll give us back a list of files that have been changed, and we will use the files and only the files to identify in that coverage data which tests touched these files, and therefore those are the tests that need to be rerun. This is definitely one of the largest gaps in testtrim's implementation today, which is that file-based coverage is going to be very coarse. It will overestimate the number of tests that need to be run as opposed to something more specific, but it's also very easy to implement, so it's a good starting point for this implementation for now. Compute relevant test cases is the interesting part here, where what we'll do is we'll go through the coverage database, and for each file that's been changed, we'll look up what tests touched those files. It also handles the cases of having new tests that have never been run before, as well as deleted tests, so there's a little bit of complexity there, but that will give us back the base set of relevant test cases. Testtrim currently has implemented some platform-specific relevant test cases. In the case of Rust, the platform-specific relevant test cases are test cases that we can identify needing to be rerun because of a change in a dependency of the Rust project. So if you imagine upgrading a Rust dependency, let's say you're using the regex library version 1.0 today, and then you upgrade it to 1.1, there will be no changes to the source files, assuming that it's a compatible change, in your actual Rust code, but there would be a change to your lock file, your cargo lock file. And so in order to do platform-specific relevant test cases for Rust, what we do is we look at the cargo lock file from the current working directory and look at the cargo lock file from the ancestor commit, find out what dependencies changed, and then we'll use that to also look up in the coverage database which tests touched these dependencies, and those tests also need to be re-executed. In the end, that gives us the relevant test cases. So those test cases will be sent over to the test platform to be executed. For Rust, what that means is we're going to go through each of those test cases, and we're going to run the test binary that contains that test with the -- exact command line argument and the name of that test. But we're also going to provide Rust flags and an LLVM profile file. Actually, as I'm thinking about this, the Rust flags probably isn't relevant here because these flags are relevant when we're compiling tests, and here we're running the already compiled executable. So this environment variable is probably only needed earlier on in the test discovery. But regardless, this gives you a sense of how we're working with Rust here. We're telling it to instrument coverage data on the build commands. And then we're using the LLVM profile file environment variable to tell it, I want you to output your instrumentation data to this specific location. And we're using this profile variable argument, which we're basing off of the test identifier, the test name. We're using some Rust crates to read that LLVM profiling data, all of the points in the code that were touched by instrumentation. We're going to keep a record that this test touched this file, and later on we're going to add a record saying this test also touched this function. This is where there's a little bit more complexity here in dealing with the external dependencies that I mentioned earlier. We also have to go through and take a look if any of the files that we touched were from the cargo registry, we're going to treat those as an external dependency, and we're going to parse out the path that was there and use that to identify what the package was and the version of that package. In the end, that will give us this coverage data object. Coverage data basically is a map of this test case touched these files, this test case touched these functions, and this test case touched these external dependencies. It also contains a list of all of the test cases that were run in the test execution suite itself. And that's used in future test runs to be able to identify if tests were removed or added relative to the coverage data that we're looking at. And then what we do is we fire that over to our database to save that data. Right now, testtrim is just using a SQLite database and using the Diesel RS Rust library to communicate and work with that database. There's definitely going to be changes to that at some point in time. I think that figuring out how this data can be shared between multiple developers is going to be an interesting element of testtrim's development. I can imagine a world where, let's say, 5 developers are working on the same project. The continuous integration or continuous delivery system is generating the coverage data for commits into the master branch, and those developers are able to use that coverage data in order to run just the relevant local tests for the local changes that they're making. So a SQLite database isn't likely to be a good fit for that in the long term. It's really great for testing in the interim. Saving the coverage data is fairly straightforward on one hand, but reading the coverage database later is going to be complicated by the fact that a single commit might only have run a small portion of the tests. So if a commit ran 5% of the tests, then the coverage data from that commit is not going to be comprehensive. And later on, when you want to identify what tests do I need to run if I change this file, you want a coverage database that contains all of the 100% of tests, not just the 5% that was run from the last commit. The way that testtrim solves that problem today is that we have storage of normalized data, which represents like the real facts about the test run. So this is a schema map for testtrim. So on a specific commit, it keeps a record of what test cases existed and what test cases were run. And then for each of those test cases that were run or executed, it's going to keep a record of what files were touched, what function was touched. But then to solve the problem of a single test commit having only a small portion of the data, it also copies references forward from the Ancestor commit to create a complete coverage map. So while the commit test case executed table might contain only the 5% of executed test cases for this commit, there's also a coverage map table that contains a copy of the 95% tests from the Ancestor commit, as well as a overwritten version of the 5% of tests that were run in this commit. That's basically the project as it exists today. It identifies all the tests that you have in your project. It identifies an Ancestor commit to work off of. It loads the coverage data from that Ancestor commit. It uses that data as well as what changes you've made to identify which tests are relevant to run. It runs those tests, and it saves the coverage data for the new commit, as well as generating a comprehensive coverage map that contains data from both the Ancestor commit and the current commit. So, how effective is it? Well, my approach for analyzing how effective this solution is to work with projects that are open source that have a good commit history and run testtrim against them to see what kind of outputs I get, how many tests need to be executed on a per commit basis. Right now, the data looks pretty promising, but there's more analysis to be done, of course, and more testing to be done. The two major ones that are test samples for me are ripgrep, as we mentioned earlier, and Alacrity, a terminal emulator. I've gone into some depth with Alacrity what I've been able to discover is analyzing the past 100 commits from the project, excluding a few commits that at the time testtrim wasn't able to run or wasn't able to operate on average, each commit only required running 8.4% of the test suite. And the P90 of tests to run per commit, so this means that 90% of commits required this many tests or less, was 38.9% of the tests. So I think that this indicates, even though it's in an early stage of development with a lot of limitations and restrictions, there's a really interesting potential gem here. If the average test to run per commit can stay around the 8 to 10% level, that does mean 90% of tests don't need to be run. If I think back to that project with 24 hours of tests, if I only had to run 10% of them on average. But let's talk about the limitations. Where is testtrim at as a project? I imagine software somewhere on like a spectrum from twinkle in a developer's eye to Microsoft Word that has been around for decades. Some of the labels that are used in between that are commonly used, like alpha software and beta software. testtrim is closer to twinkle in a developer's eye than it is to an alpha software release. It probably even hasn't completely reached the point of proof of concept. I think it's at the stage of concept is interesting and there isn't any strong evidence against it yet. So it's not proof of concept, but it's like hypothesis of concept. Yeah, I'm going to say it's at the hypothesis of concept stage. What is between hypothesis of concept and, a beta release? Let's split this into small technical items that testtrim would need to address in order to be usable within a small scope, and large technical items. On the small scale technical items, before testtrim could be used even with Rust projects and even with just projects that only do local testing, testtrim just doesn't have the performance that it needs to do that well. And the main thing isn't the functionality in testtrim, but it's the fact that testtrim runs the tests one by one serially, whereas like the cargo test runner runs tests in parallel with a larger scale testing strategy. So even if you were just developing a Rust project today and you're using testtrim, it would actually perform slower than running cargo tests directly. I think that's a solvable problem, so I'm not super concerned about that. On Rust test projects, I've found today that testtrim doesn't work on all of the large Rust code bases that exist today. So I wanted to understand a little bit more about what exactly isn't working there. There's something about the test execution environment that varies. That is also, to me, likely a solvable problem. Those are like the technical pieces. If I solved those, I would have a usable tool for a Rust project. The larger requirements for testtrim to be a really useful tool are going to be supporting multiple different platforms. So not everybody's doing Rust development, but I don't see any reason that the same concepts couldn't apply to, for example, JavaScript development. But I don't want to dig too much into those. I don't want to get really broad in testtrim's capabilities before I get really good at some of the smaller scope. But the major thing, right, where testtrim is really going to add a lot of value is if I can get it working with distributed testing environments. So when you have test code running on one system and it's operating a browser, and that browser is touching front-end code, and that front-end code is touching back-end code, and that back-end code is touching database code, is it possible to use the same concept of coverage-based test targeting in a complex distributed environment? I think it's going to be possible, but quite difficult. That's where testtrim is really going to unlock a lot of value, because those tests are the ones that are going to be really expensive for projects to run. So that's the technical restrictions on the project today. And then that's the list of things that I want it to be able to do for it to be really useful. And then the third thing is really going to be ultimately, how effective can it be at what it's trying to do? And how effective does it have to be for it to be something that people want to pick up and use? So that's kind of a cost-benefit analysis question. Let's imagine that the results of 8% average test run per commit is how effective it can be in all cases. That'd be cool. I like 8% sounds good. But then how expensive is it going to be to implement? How complex is it going to be? How much more complexity does it add to the continuous integration system that you're running it on? What is the time that it takes to build that solution into a project? And what is the cost in terms of operating the testtrim system and having a centralized database where all of this coverage data goes? If the costs are too high, then even with that 8% targeting metric for benefit, you're going to have a poor cost benefit analysis. And so I don't know how effective it actually has to be for it to be useful to people. That's kind of a project risk. Ooh, all right. That is a run through of testtrim, what the concept is, what the software does today, and some of the things that I think are blocking it from being a usable project and going forward and revolutionizing automated testing. My plan right now is to spend basically a week doing development of testtrim, putting new features and new capabilities into it, solving problems that it has, and then maybe a week developing a new video like this as I dig through some of the technical details of what I've been working on, and I publish that for everybody to hear for their entertainment, their consumption, their interest. I don't know, whatever reason people watch videos here. I would love it if you would subscribe to this channel to see those future updates. I think they're going to be really interesting content. I'm really excited about this project. I think it has a lot of potential to be really valuable for people, for businesses, for projects. So please subscribe, come along and go through this journey with me. Provide me your feedback, your insights, and your input, because the more I know about what people think about this project, the more I'll be able to tailor it to what people's real needs are and real challenges, as opposed to just working off of my historical challenges. Thank you for watching, and see you later.